So let's start our discussion of Laplace's equation. And so we'll introduce the Laplace's equation and look at some solutions in one dimension. We've done this before, but let's take a look at how we do this derivation. And the first equation that we'll derive is called the Poisson's equation. And we start with the Maxwell's equation number 1, which is the divergence of E at the position r vector is equal to rho at r vector divided by epsilon 0. This is an equation which is defined at a particular point. Well, we know we can represent E in terms of a gradient. We can take minus the gradient of V for E, so that's what we have right here, and substitute that into our divergence equation. We have del dot and then minus del V. Bringing the minus sign out, we have this operator here, which is del squared. What that means is del dot del operating on the function V. Bringing the minus sign over to this side here, we then have Poisson's equation, which just says that del squared V is minus rho over epsilon 0. Realize that this is non-zero only where we have charge. Many times there's regions of space where there is no charge, and so this side is equal to 0. When we have this equation, that's called Laplace's equation. This del squared operator is called the Laplacian. In Cartesian coordinates, if you take del dot del, you'll end up getting the sum of the second derivatives with respect to x, y, z. So we set that equal to 0. In cylindrical and spherical coordinates, it's a little more complicated, but you can see that you get a term that looks like it's related to rho, you get a term which is related to phi, and a term which is related to z. And similarly for spherical coordinates, the operator looks like this. For the r derivatives, here's the theta derivatives, and here's the phi derivatives. And the solutions to these equations, the Laplace equation for different coordinate systems, are called harmonics. One way to think of it is that if you have a solution that, for example, is sinusoidal, say sine kx for different k, then those will be harmonics, and that will generate a whole series of functions. This equation appears in other branches of physics, and probably the most predominant one is fluid mechanics. And you recall that we often talked about E-fields flowing through space, and that analogy comes from looking at fluids. So if we solve Laplace's equation just by itself, we end up getting arbitrary constants, which we don't really know what they are. To find those, we have to have something like boundary conditions, and the two together determine a solution. There's a uniqueness theorem that is in vogue for the Laplace's equation, and it says that if you find a solution, then it is the solution. This uniqueness often helps us find the solution we want. Let's consider an empty space surrounded by some electrodes that are at particular potentials. So normally these are things like conducting surfaces with known potentials attached. For example, suppose we have these two conducting objects here. We hook them up to a battery. I've grounded this. It's not necessary to do so, but if we do, then we really know what that potential is. It's 0 volts. And the battery will raise the potential of this object up to delta V. That's the battery voltage here. And the way I've shown it, this is plus and this is 0 volts. So what we're interested in is finding the potential at positions that are outside of these two objects. So here, over here perhaps. And so that's what we're trying to do. And Laplace's equation in principle can do that. What happens then is these electrodes with their potentials provide the boundary conditions for solving completely Laplace's equation for the surrounding empty space. Well, let's consider Cartesian coordinates, and we're only going to consider one-dimensional problems, so we only have an x dependence. In that case, Laplace's equation is pretty simple. It's just the second derivative of v with respect to x squared is equal to 0, so that's the equation. So the way to solve that, there's lots of ways to solve it. One is just to guess the solution. But here we have u being the first derivative of v. Then if you take the derivative of u with respect to x, you'll get the left-hand side of Laplace's equation. If you take that derivative, set it equal to 0, then you can imagine what the solution of u is, because if you have a function of x, take the first derivative and you get 0, then it just means it's a constant, and we'll call that constant m. U is equal to m. Now we have m equaling to the first derivative, so we can divide that up into dv equals m dx. And the solution to that one-dimensional equation is just a linear equation, mx plus b. That's the equation of a straight line. The slope is little m, and y is the intercept. If you just wanted to put that into Mathematica, you just use dsolve, which solves differential equations. Here's Laplace's equation here, and you're asking it to solve that equation for the function v of x, and the variable is x. So that's the command for doing that. Well, here's the answer. V of x is equal to a constant plus x times another constant. So this would be m, and this would be b. So the two constants, at this point we don't know them, and so we have to use the boundary conditions in order to find them. What we're really talking about here are cases where we have two potentials, say V1 and V2, at positions x1, x2. And so that's the same thing as, say, the parallel plate capacitor. So at x1 we have V1, at x2 we have V2. This dimension here is infinite. The dimension in and out of the paper is infinite. X is the only variable. You're talking about the solution in this space over here. We could argue that if these are conductors, we know that the field over here and the field over here is 0, and also the potential would just be constant, which we could take as 0. X equal to x1 gives us a potential V1, and x equal to x2 gives us the potential V2. So those are our boundary conditions. Let's write v of x like we did before, mx plus b. We set vx1 equal to mx1, so we're just evaluating this at x1 plus b is equal to that value, v1. V of x2, the same thing. You have mx2 plus b equals v2. So we solve those two simultaneously for m and b. We have m expressed in terms of the two potentials and the two positions of the electrodes. B is a function of v1 and v2, x1, x2. Then if you put that into your final equation, this is the complete solution of the problem given v2, v1, x1, x2, and so on. So let's take a look at some of this with Mathematica. Okay, so we'll go up here. Repeat what we said. Here's the expression for Laplace's equation. It's the second derivative of v with respect to x equals 0. Same boundary conditions that we discussed earlier. We expect a linear solution, and to do that I'm going to use the same concept of getting the solution that I showed you before, just to repeat that, and so we'll evaluate this to see what we get. Here's the general solution without any BC's. It's just like what I showed you before. C1 plus xc2. If we wanted to, we could put in the boundary conditions for these like we did before, but Mathematica can actually solve the differential equation with the boundary conditions. And the way you do that is you see this curly bracket to curly bracket. You put in the equation, the differential equation, and then you put in the boundary conditions, which are shown here. And one little trick to remember is the double equal sign. And again, you're solving this for v with the variable x. Here's our general solution with boundary conditions for the parallel plate system. It might not look exactly like what we have, but if you take and factor out the x so that you have v1 minus v2 divided by this times x, that will be your m, and then b would be a plus this quantity here, this quantity here divided by x1 minus x2. So indeed we get the same solution. Okay, so I'd like to show you a plot of this. It's very simple because they're straight lines, but we're going to look at it for different values of the boundary conditions. I'm going to choose numerical values for the positions, so I'll put x1 at 0 and x2 at the number 10. I could put anything here, but let's use those. when we do that, we end up getting this plot. Let me show you what it looks like. These are the two values of the potentials, and V1 is applied to an electrode at 0, and V2 is applied at the electrode at x equals 10. So this is x2, this is x1. Well, right now I have this at -5 and -5, and so the two ends of the solutions have to be at -5 because they have to be at the boundary conditions. And then whatever happens in between is the solution that we got for Laplace's equation. Well, let's see. Why don't we just take V2, take it up to +5, and so you can see you get this line here. If you bring V1 up to +5, well, you have the same issue that you had below. It's just a straight line that's constant from the two potentials. And then you can have anything in between like that. So that's pretty simple, but it does give you a feeling for the way this solution would go if you change the potentials in any way you want. Okay, so that's the case of Cartesian coordinate solution to Laplace's equation. If we have this solution, and here's what we found before, then there's a couple of observations which we need to make. And the first is that for any range d, plus or minus d, within the region of a solution, so if you bound the particular point on the solution and go plus or minus d, you're going from a value of the function here and a value of the function here, and this is the value in between. So over this range here, we end up getting this expression here where we have the potential at the point x in terms of the potential at the two endpoints of this interval. It will be equal to 1/2 times the sum. So it's the average of these two values. And so if you come up here, you can see that this value and this value, this one raises up this much, this one falls this much, those are equal, and so you end up getting the average being this point right here. This is a trivial result for the straight line. It's going to be a useful result later on. If d is small, it's also true in any other coordinate system. The dimensions that we're talking about can be 1, 2, or 3 for real problems. This concept here extends to 2 or 3 dimensions. It's useful for using computers to solve numerically Laplace's equation. The second observation is there are no local maxima or minima within the region of validity of the equation. The maxima and minima can only occur at the boundaries. So here's the maximum for this function, here's the minimum, and the places where that occurs are the boundaries. They do not occur in the region in between. For a straight line that's obvious, but later on we'll see how that works for other coordinate systems. So if you look at the way this comes about, suppose you have a function that has a maximum between the boundaries. So this would be x1, this would be x2 for some other solution that gives you this curve here. Let's apply this observation here that we're supposed to get the average of the 2 points. Let's take these 2 points right here. So this is minus d and plus d about this value of x. So if you look at this, the average value for these 2 points that we picked, I chose it on purpose that they're equal. And so the average value is right here. But this is the actual point. We violate this expression here. Our conclusion then is that this expression here is not true. I put 3 stars here just to show you that that's the expression. So we conclude that this is not a solution of Laplace's equation. Indirectly then, that any solution that has a maximum or minimum between the endpoints cannot be an actual solution of Laplace's equation. Well, how do we look at this in terms of the calculus? If this is a solution to Laplace's equation, phi, we can identify extrema, so min-max, by the fact that they have a 0 slope. You know that if you have a curve here and it has a maximum, the slope at that point is 0. To find the type of extrema, in terms of is it a min or a max, we use the curvature. And the curvature is the second derivative. So if you have the second derivative less than 0, then you have a maximum, and if you have the second derivative is greater than 0, then you have a minimum. And the way I remember that are these funny little figures, that if you have a negative second derivative, you have a maximum, so that's this point right here. If you have positive second derivative, you have a minimum, which is this point here. The smiley face and the frowny face tell you which is which. For Laplace's equation, we know that that derivative is equal to 0. So therefore, there are no extrema except at the boundaries. So that's the conclusion we come to.